Alright, so let us recall what we had done in the previous class. So the ideas were that you have A which is an n cross n matrix, alright. Then you had a x which was non-zero such that Ax is equal to lambda x, x not 0. So that gave me eigenvalues, eigenvector. So lambda is eigenvalue and x corresponding eigenvector. Fine. And we had said that lambda comma x is an eigenpair. Then there was a notion of what is called algebraic multiplicity of eigenvalue of lambda as an eigenvalue of A. So this was the multiplicity of root city of lambda as a root of the characteristic equation. So the equation, if you remember, it was nothing but determinant of, you can write xi minus a is equal to 0, a polynomial equation of degree n, alright. So it has n roots over complex numbers, and we are looking at only everything over complex numbers, fine. So you are assuming that lambda is an eigenvalue, and then you are looking at algebraic multiplicity. If lambda is not an eigenvalue, its algebraic multiplicity will be 0, it will not be a root of the characteristic polynomial, fine. So now we had notion of what is called a geometric multiplicity of lambda as an eigenvalue of A. So geometric means some space has to come. So therefore this was nothing but the dimension of null space of lambda I minus A. That was the dimension, alright. And what we showed at the last thing that we showed yesterday was last part was that geometric multiplicity of lambda as an eigenvalue is always less than equal to the algebraic multiplicity of lambda, fine. This is what we showed, that was the last thing we showed. And the idea was very simple, which we have been doing again and again in some sense, that we take a basis of this, take a basis of null space of lambda I minus A, fine. Once we have taken a basis, so let the dimension be k, so basis, and then we make it orthonormal basis. There is no need for this, not orthonormal basis. We do not need it at this stage, but in general sometimes we will need it, fine. Once you have taken a basis of this, extend it to form a basis. So take a basis u1 to uk of this, we can make it ordered basis. So there is a bracket that comes into play here that we have ordered basis, fine. Extend it, extend to get an ordered basis u1 u2 uk plus 1 to un, a basis of Cn over C, fine. Once we have done that, then we looked at, so we take this as it is, this is our ordered basis B. We want to look at the matrix, want to look at the matrix of A with respect to the ordered basis B. So there were two ways of writing it, understanding it. One was that we did yesterday was we defined P as u1 u2 uk plus 1 till un, and we computed P star AP, we computed, and we took orthonormal basically because we wanted to compute P star AP, because if B is an not orthonormal basis, then the matrix P, so if UIs form an orthonormal basis, then the matrix P that I have defined here, P is unitary, and P is unitary implies P star is same as P inverse. All right, fine. Is that okay? So we had this idea that P star is same as P transpose, not inverse. It's not only that, unitary. So P star is P inverse, or let it be. All right, fine. And then from there we wrote it as P star. We put A inside, so we got A of U1 till A of UK plus 1 till A of UN. This was nothing but P star of A of U1 was lambda 1 U1, or say you are fixing lambda here, so let it be lambda itself, lambda U1 till lambda UK, and I don't know what we have here. There are some things that we do not know. So when I put in P star here again, so what we are saying is P star is P inverse, you just have to multiply by it, fine. So just look at P star, so P star into P is identity, so P star times P is your U1, U2, UN will give me P star of U1, P star of U2, P star of UN, and since this is identity, fine, I sub n, what I get is this is the first, so 1 0 0, this will be 0 1 0 0 0, and this will give me 0 0 0 1. All right, fine. So this is what I will get. So what you see here is that you got here P star U1 here, so I will get here lambda 0 0 0. Again it will be here, which will be P star U2, therefore again I will get 0 lambda till 0, fine. This will give me 0 0 0 k, sorry 0 0 0 lambda, fine. So this part is taken care of, so this part is fine, there is no problem because everything here is 0 for us. Now this part I do not know what it is, do not know, I don't have any information about this part, so I cannot do anything, I can just leave it as it is. Some say C here and B here, this is what we do, fine. And therefore when I want to compute, so want to compute the eigenvalues of A, we need to look at determinant of xi minus A equal to 0, which was same thing as saying that we saw that the determinant of P star, or which is same as xi minus P star AP equal to 0, which will again imply that these lambdas will give you lambda 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 k times, and lambda may appear, I am not sure what it will happen or what, but lambda may appear as a root of xi minus b, determinant of this is equal to 0. All right, fine. So I do not know about this part, so the lambda can be more, so algebraic multiplicity can be more. All right, so this is what we wrote here, that algebraic multiplicity can be more because this can come from some lambdas can appear from B. All right. So this is what we had, and this is what happens in most of the examples when we look at what are called nilpotent matrices. So if I look at the nilpotent matrices, nilpotent matrix, all right, what we have is nilpotent matrix means A to the power n is 0 for some n belonging to the natural number, all right, and therefore, So this implies all its eigenvalues are 0. Fine. So I would like you to show as an exercise, show that there exists a non-zero vector x such that the matrix of A with respect to a basis generated using x and things like that. There is a question mark that I need to put because I have not made my statement completely correct. All right. It looks like zeros here on the diagonal, and off diagonal there will be some ones here, somewhere ones here, and so on. All right. So we have taken an example for you. If you remember, we had a matrix here, say right, 0 1 0 0 0 1 0 0 0. For example, I can take this. So I can, for example, I can take this matrix which is of the size 4 plus 3 plus 2 is 9 cross 9 matrix, and you can say it is nilpotent. And not only that, you can see that if I write this as A, then A to the power 4 is 0. All right. So there is a notion of what is called the degree of nilpotency or index of nilpotency, and accordingly you can build up. Fine. So I will not get into that part for me because that is going out of the syllabus. There is what is called a Jordan decomposition. Fine. But what you can show, if you say that, so let A be n cross n such that A to the power n minus 1 is not 0, but A to the power n is 0, will imply A with respect to a basis B, there exists a basis B which comes from the previous idea itself. This x will look like 0 1 0 0 0 0 1 0 and so on. So 0 will be on the diagonal and 1 here. All right. So this is the way it will look like. You can do it yourself, you can try to prove it yourself. Fine. So I will not get into that part, but you can do it. And here in this case you can see that the algebraic multiplicity of this is n, algebraic multiplicity of 0 as an eigenvalue of A is n, but if you look at the geometric multiplicity of 0 here, this will be just 1. All right. In this example, if I am looking at this example, this A, then the algebraic multiplicity of 0 as an eigenvalue of A is 9, because it is a 9 cross 9 matrix with zeros on the diagonal. It is an upper triangular matrix, but the geometric multiplicity here is 3. One coming from here, one from here, one from here. All right. Fine. So you can check here that E1 is there with you, which will give you an eigenvector. Here this will be E4, and here it will give you, so 4 and 6, so it will be E7, 8, 9, 10. Yeah. So these will be the eigenvectors E1, E4 and E7. These will be the eigenvectors, and those are the only eigenvectors. All right. So I have given you idea of this. So let's go back. So the idea was to look at this part. This is one way of doing it, which is P star AP. Fine. The other way will be to write A as BB. All right. So I think I should write. So the other way will be to look at A of BB and then do things. So let me write that also with respect to, so my P remains the same. So ABB and that is my B. So let me write that part. So my P, so my B is U1, U2, UK till UN. I want to get the matrix of A with respect to B. All right. So if I want to get this, what I am supposed to do is, recall we did everything with respect to linear transformation, but you can do with matrix also by defining T of x is equal to AX. So you can just look at A of U1, A of U2, A of UK, A of UK plus 1 till A of UN, fine. But to get the matrix, we need to evaluate with respect to B, we need to find out the coordinates with respect to B. So we need to find out this B, this is what you need to do. This is same as A U1 is lambda U1 with respect to B, lambda U2 with respect to B, lambda UK with respect to B, and then I do not know what they are, as I said earlier also in the previous part, that I do not know what they are, so I can just leave it as it is, fine. And this in the ordered basis B itself, U1 is the first vector, so it is nothing but lambda 0 0 0, lambda U2 is the second vector, so it is 0 lambda 0 0 0, fine. So whole 0 here. Similarly, this UK will give me 0 0 0 and lambda here, fine. So this whole thing is 0 for me. I do not know what I have, but it is some matrix B, and therefore you can see that either you write like this or you write it as P star AP. The two ideas are same. We are looking at writing a matrix with respect to the ordered basis, and the other is trying to look at similarity. They are same and nothing else. There is no change. The ideas are same, but you write it in a different way. That's all. Fine. So now we go to the next idea, what is called diagonalizability. So definition: A n cross n. Remember that we have done LU decomposition, rank decomposition, QR decomposition. Then the next idea was diagonalizability, that when can I diagonalize the matrix. So let A be an n cross n matrix, then A is said to be diagonalizable if there exists an invertible matrix P such that P inverse AP is D, a diagonal matrix. All right, that is the definition. So if you look at the previous one, in the previous example what we had was, we had P star AP, we looked at this part, and this was related with what is called looking at A of B comma B, fine. Similarly here also the same idea comes, because P star was nothing but P inverse. So here also is the same thing that I want, so I can rewrite this, so rewrite it as, so I am rewriting the definition, as there exists a basis, an ordered basis, this is of Cn over C, such that there exists an ordered basis BC such that A of BB is equal to diagonal matrix. All right. So we will look at some examples later on, but first let me look at the idea behind it. All right. So let's look at the idea. So idea. What are we saying exactly? We are saying that P inverse AP is diagonal. All right. This is same thing as saying that AP is equal to PD. Fine. So look at P and write it as, say, some U1, U2, Un. It is an n cross n matrix. I can write like this, everything over Cn over C. So it is just a column vectors of complex numbers. So I can write P as this. So let's compute this, both the sides. So what is AP? So therefore AP, this implies it is nothing but A times U1, U2, Un is equal to U1, U2, Un times the diagonal matrix. Let me write the diagonal matrix as D1, D2, Dn. This is 0, this is 0. So now I can look at this, which is same thing as saying that A of U1, A of U2, A of Un is equal to, now this diagonal matrix is being multiplied on the right, so it is nothing but column transformations. So it will be nothing but D1 U1, D2 U2, Dn Un. All right. So important, please understand, I am writing P as this, I have only done P writing like this. After that it is all equivalent conditions. AP equal to PD is equivalent to this is equivalent to this, alright. Again this will be equivalent to saying that A of U1 is equal to D1 U1, A of U2 is equal to D2 U2, and so on. A of UN is equal to Dn UN. So what we are saying here is that, which is same thing as saying that I have got D1 U1, D2 U2, Dn UN as eigenpairs, distinct. Di's need not be distinct. We are not saying that, fine, but we are saying that I have got n linearly independent. So if I look at these U1, U2, Un, they are columns. So these are columns of P, an invertible matrix. So P is an invertible matrix, very important. So they are columns of P, they are invertible, and hence they are linearly independent, implies UIs are linearly independent. Or what we are saying is that A is diagonalizable, A is diagonalizable if and only if we have n linearly independent eigenvectors. Look at the definitions. So we had here, these are the eigenpairs. So you have got U1, U2, Un, you have got n linearly independent eigenvectors, alright. So A is diagonalizable if and only if we have got n linearly independent eigenvectors. And what is this n? N is the size of this matrix. A was n cross n, alright, it was the size of the matrix, fine. This is one way of understanding it using matrices. This is what we wrote, fine. Or if I want to write in terms of our basis idea, so I can take my B here that I want to look at is nothing but U1 to Un itself. So I take my ordered basis as this, ordered basis. So when I want to compute A of BB, I am supposed to look at A of U1 till A of Un and then evaluate each of them with respect to B. This is what I am supposed to do. So if I look at this, I am supposed to look at this itself, fine. And once I have done that, I am only supposed to look at with respect to B here, with respect to B, with respect to B. So this again with respect to B, this with respect to B, this with respect to B, and this is nothing but D1 1 1 1. So if I want to go further, so this part, or I think there may be some problem, so clarity. So let me write here. So A of, so I'll have to compute A of BB will be equal to A of U1 till A of Un with respect to B, which will be equal to D of U1 with respect to B till D of Un with respect to B, which will be equal to D1 0 0 0, 0 D2 0 0 0 and Dn here 0 0 0. So it is a diagonal matrix. Diagonal matrix with entries D1, D2, Dn. Fine. This is what we wanted here. See here, this is what we wanted, that we have a diagonal matrix with diagonal D1, D2, Dn. Fine. So what we are learning here is that whenever we have something is diagonalizable, it means that I have an ordered basis with respect to which the matrix is a diagonal matrix, or we have n linearly independent eigenvectors, fine. So that's important, you have to keep track of things. So now let me look at examples. So I just need to find linearly independent, enough number of linearly independent eigenvectors, alright. So the first example, you already have that. If I look at this matrix 0 1 0 0, fine, we have only one linearly independent eigenvector, which was E1, alright, this was the only one, fine, which is corresponding to 0. corresponding to 0. All right. So let's try to show that A is not diagonalizable. So claim A is not diagonalizable. So how will I do? Suppose A is diagonalizable. On the contrary, suppose A is diagonalizable, implies there exists a non-singular matrix P such that P inverse AP is diagonal. All right. Now this diagonal matrix and this P inverse AP, they are similar matrices, so they are supposed to have the same eigenvalue. All right, fine. So A is nothing but PD. So writing D here, the P inverse. All right. So this implies A and D are similar, implies they have the same set of eigenvalues. What are the eigenvalues of A? This implies the eigenvalues of D are 0, 0 as eigenvalues of A are 0, 0. Fine. So since D is a diagonal matrix and eigenvalues are 0, so D must be the 0 matrix. This implies D has to look like 0, 0, 0, 0. This is what we saw in the previous slide. If you see that D1 to Dn were the eigenvalues. All right. So whenever I have a diagonalizability, then D1 to Dn are eigenvalues. Fine. And therefore what I get here is that this will imply that A will look like P times 0 matrix times P inverse, which is the 0 matrix, but A is not 0, which is not equal to 0, 1, 0, 0, which is A. All right. So there is a contradiction. Similarly, I would like you to check that if I write A as 2, 1, 0, 0, 2, 0, or let me write one more here. Fine. So 0, 1, or say 3, 1, 0, 3. If I write this matrix here, 0 here, 4 cross 4, A is not diagonalizable. So think about it, why it is not diagonalizable. Just so diagonalizable. So try that out yourself. Fine. I would like you to also show that this is a bit difficult for you, but you can show that this matrix A, which is 2, 1, 0, 0, 2, 1, 0, 0, 2, this is not diagonalizable, because diagonalizability implies A is equal to P D P inverse, which will be P times D eigenvalues here. So it will be 2, 0, 0, 0, 2, 0, 0, 0, 2 times P inverse, which is 2 times identity, which is not A. All right. So why should you get this as the diagonal matrix? Think about it. I want you to understand that. That's very important for us. And we end this lecture with this idea itself. All right. Thank you.